guys, today we are going to talk about Ian Stewart's Nature's Numbers, Chapter 4, The Constants of Change. For a long time, there have been two opposing views on how we see nature. The first view is that the universe obeys fixed, immutable laws and that everything is in a well-defined, objective reality. On the other hand, the second view is that there is no such thing as an objective reality, that all is flux and all is change. The advancement of science has been largely governed by the first viewpoint. However, there have been an increasing sign that the prevailing cultural background is starting to switch to the second way of thinking. Different scientists like Newton, Galileo, and Kepler realized that change obeys rules. Not only can law and flux coexist, but law generates flux.
Why is it that we land on the ground instead of floating off into space? It is because of gravity. What is gravity? We all know that gravity is something that pulls everything towards the ground. Or simply, it is a force exerted by the earth to pull objects towards it, including you. Without the force of gravity, there would be no life on earth. Air, water, animals, everything would fly off into space. There will be no you, no me, and nothing. Think of gravity like the invisible superglue that holds our massive world together. You cannot see it, but it's always there. Isaac Newton was the first person to seriously study gravity over 200 years ago. He imagined firing a cannon from the top of an extremely tall mountain. Isaac Newton knew that the cannonball would travel in a straight line at a constant speed forever. But, gravity pulls the cannonball downward. He realized it doesn't matter how heavy an object is either. No matter where you throw the cannonball, it's going down. Gravity is the cause that produces the effect of all unsupported objects falling down. The ball will go up or to the left or to the right for a little bit, but eventually, it's going to be pulled back down to the ground no matter what. Gravity's got a hold on, well, everything. How can we explain this constant that is hiding among the dynamic variables? When all else is flux, why is the acceleration fixed? An Ian Stewart book of Nature's Numbers states, one attractive explanation has two elements. The first is that the Earth must be pulling the ball downward. That is, there is a gravitational force that acts on the ball. It is reasonable to expect this force to remain the same at the different heights above the ground. Indeed, we feel weight because gravity pulls our bodies downward, and we still weigh the same if we stand at the top of the tall building. Of course, this appeal to everyday observation does not tell us what happens. The second element of the explanation is the real breakthrough. We have a body moving under a constant downward force, and we observe that it undergoes a constant downward acceleration. Suppose, for the sake of argument, that the pull of gravity was a lot stronger. Then, we would expect the downward acceleration to be a lot stronger too. The simplest theory, consistent with this mixture of real experiments and thought experiments, is that when a force acts on the body experiences an acceleration that is proportional to that force. And this is the essence of Newton's law of motion. The only missing ingredients are the assumption that this is always true for all bodies and for all forces, whether or not the forces remain constant, and that identification of the constant of proportionality as being related to the mass of the body. To be precise, Newton's law of motion states that mass times acceleration is equals to force. That's it. Its a great virtue is that it is valid for any system of masses and forces, including masses and forces that change over time. We could not have anticipated this universal applicability from the argument that led us to Rome, but it turns out to be Newton stated three laws of motion, but the modern approach views them as three aspects of single mathematical equation.
Canon motion of Galileo Galilei. Was an Italian astronomer, physicist, and engineer, sometimes described as a polymath from Pisa. Galileo has been called the father of observational astronomy, as the father of modern physics, the father of the scientific method, and the father of modern science. So let's talk about emotions in two-dimensional projectile motion. We have straight line motion, whereas a car is moving horizontal motion along straight path, and a stone falling vertically from the third floor building to the ground. But now, how about objects experiences horizontally and vertically at the same time? Suppose you're firing cannon in some kind of angle. The cannonball will fall parabolic path during its flight before which is the ground. We will try to understand the movement of the cannonball. First is velocity. Initially, the cannonball has initial velocity. This initial velocity can be resolved to its x direction as and y direction as. This means the cannonball is moving upward while moving to the right. We have the acceleration. There is no other acceleration governing to this kind of motion, but only the acceleration due to gravity, which is equal to 9.8 meters per second squared. This acceleration is pointing downward and is constant during the cannonball flight. Last, we have the distances. There are only two distances which we should give attention. This is the maximum height when cannonball's velocity along y direction is 0, and distance traveled of the cannonball during its flight.
When you hear the word Newton, what comes first into your mind? Is it motion, gravity, or the apple that falls from the tree? Well, your thoughts are correct. However, you know that together with Gottfried Leibniz and Isaac Newton was invented the calculus.
So, what is calculus? Calculus is all about studying the rate of change of quantity over time. In particular, it can be narrowed down to the study of the rate of change and summation of quantities.
Together, they discovered that the
Differentiation gives us to understand phenomena that involves the rate of change. For example, if you own a motor car, you might be interested in how much of change in the amount of fuel in your tank is accompanied by a small change in the distance you have traveled. The integration integrates the small pieces together and tell us how much something is made overall by a series of changes. Other examples that exist in real-life situations include spread of disease, weather and climate prediction, traffic flow, financial markets, population growth, water pollution, chemical reactions, suspension bridges, brain function, rockets, tumor growth, radioactive decay, airflow across a plane's wings, electrical circuits, planetary motion, and vibration of guitar strings.
But whether it's realization or integration, both categories involve the idea that we can infinitely many times and get a final answer that is useful. Both categories involve dealing with things that are infinitely small or infinitely close together.
Newton's law of gravity is a well-known inverse square law. So, what is inverse square law? The inverse square law proposed by Newton suggests that the force of gravity acting between any two objects is inversely proportional to the square of the separation distance between the objects' centers. Altering the separation distance results in an alteration in the force of gravity acting between the objects. Since the two quantities are inversely proportional, an increase in one quantity results in a decrease in the value of the other quantity. Let me illustrate the idea. If this is our source of gravity, then the light is the force of gravity, and then this is our object. That is, an increase in the separation distance between the object and the source of gravity causes a decrease in the force of gravity, and the decrease in the separation distance causes an increase in the force of gravity. That is the inverse square law.
The motion of the Moon, Earth, Sun system is said to be a three-body problem for evidence reasons. It is so unlike the nice, tidy two-body problem Newton solved that it might as well have been invented on another planet in another galaxy. There are 58 nature's numbers or in another universe. The three-body problem asks for a solution of the equation that describes the motions of three masses under inverse square law of gravity. The mathematicians tried to find such a solution for the centuries but met with astonishingly little success beyond approximations, such as Delaunay's, which work only for particular cases like Moon, Earth, and Sun. Even the so-called restricted three-body problem, in which one body has a mass small that can be considered to exert on force at all, can be upon to the other two provided utterly intractable. It was the first serious hint that knowing the laws might not be enough to understand how a system behaves, that the curves between laws and behavior might not always be bridgeable. Despite intensive effort, more than 3 centuries after Newton, we still do not have a complete answer to the three-body problem. And then, he did far more, by showing such a system can exhibit a strange phenomenon known as Arnold diffusion. The first discovered by Vladimir Arnold of Moscow State University in 1964. So Arnold diffusion produces an extremely slow, random drift in the relative orbital positions. This drift is not truly random. It is an example of the type of behavior now known as chaos, which can be described as apparently random behavior with purely deterministic causes. Notice that this approach again changed the meaning of solve. First, the word meant find a formula. Then, it's the constant of change 59, meaning it changed to find approximate numbers. So, finally, it has in effect become tell me what the solutions look like. In place of quantitative answer, we seek qualitative ones. If it is too hard to find a formula, try an approximations. So, if the approximations aren't available, try a qualitative description. But it is wrong to see this development as retreat. For what this change of meaning is thought as is that for question like the three-body problem, no formulas can exist. We can prove that there are qualitative aspects to the solution that the formula cannot capture. So, the search for a formula in such questions was a hunt for a mare's nest. So, why did people want a formula in the first place? It's because, in the early days of dynamics, that was the only way to work out what kind of motion would occur. Later on, the same information could be deduced from approximations. Nowadays, it can be obtained from theories that deal directly and precisely with the main qualitative aspects to the motion.
Ian Stewart's book, Nature's Numbers, lets us see the world in a mathematical way. It conveys the wonder and strangeness of the world in terms of patterns and shapes, numbers, and math. The world is full of clues and information which can lead us to deeper and deeper appreciation of the patterns and harmonies all around us. He expounded that Newton's basic insight was that changes in nature can be described by mathematical processes, and that calculus helps us to work out solutions to moving bodies. The meaning of solve has also changed over time, from finding a formula to finding approximate numbers. Ian Stewart provided us with insights in understanding nature's patterns in their own terms, in qualitative terms, and not just mathematical processes.